Hello, it's Stat 134, Lecture 35. Last time we talked about the conditional probability in the continuous case. This is section 6.3, in particular the conditional density, which has the formula shown here. You can visualize what the conditional density is by taking a slice for a specific x of the joint density. The probability that y is in dy, given that x, is the shaded red region in the joint density, in the conditional density picture. And the probability that y is in dy is summing these areas for different slices along x and summing them all together with an integral. So that's going to give you a volume. That's the idea of an integral conditioning formula. A major example of conditional densities is in Bayesian statistics, where we have posterior and likelihood densities. For example, x is the uniform 0, 1. I1 given x is x, and I2 given x is x are IID Bernoulli x. Now, here I1, for example, is 1 if you flip a coin and it's heads, and it's 0 otherwise. Now, you need to be careful here because x is continuous and I1 is discrete. Now, so when we talk about the density of x, we're going to represent that with f. When we talk about the probability mass function of discrete, we write p. So just be aware of that. So for example, if we want to find the probability of getting a heads, we would need to condition on what the probability of heads is, x. We'll use the integral conditioning formula for this. The likelihood is probability that I1 is 1 given that x is x, and this is just x because I1 is 1 given that x is x is we're looking for the chance of getting a heads when the chance of getting a heads is p or x. So it's obviously x. If you look at what we've done, we get a half. Now the posterior is the likelihood times the prior divided by a constant, the probability that I1 is 1. So this is x times 1 over a half, or 2x. Today we're going to continue with section 6.3. We're going to talk about integral conditioning formula, Bayesian statistics, and conjugate pairs. So the integral conditioning formula, we've seen that here, and let's do some examples. So let's find the probability that I1 is 1 and I2 is 1. So here we'll use the integral conditioning formula by conditioning on x is x. Now the probability that I1 is 1 and I2 is 1, given that x is x, factors by independence of the conditionals, and so we just get x times x, or the integral from 0 to 1 of x squared, which is a third. So notice that I'm not saying that I1 and I2 are independent. I'm saying that the conditionals I1 given x and I2 given x are independent. Clearly, I1 and I2 aren't independent because probability of I1 is 1, because if this factored, you would get 1/2 times 1/2, and that's not a third. So find the probability that I2 is 1, given that I1 is 1. Are I1 and I2 independent? So we'll see it another way here. Probability I2 is 1, given that I1 is 1, we'll use Bayes' rule. and the numerator is a third and the denominator is a half. So we get 2/3. And the conditional is not equal to the unconditional. So we don't have independence of I1 and I2 here. Let's review beta distributions. So the density for beta is what I've written here, and what's important is the variable part. The variable part uniquely determines the density, because the density integrates to 1. So the integral of the variable part is uniquely determines what the constant is. Okay, so if your variable part is just 1, then your random variable must be a beta 1, 1, because R must be 1 and S must be 1. If your variable part is X, then R must be 2 and S must be 1. So you have a beta 2, 1. Or if you have X1 minus X, then you must have a beta 2, 2, and so on. So for example, if X is uniform 0, 1, so we saw that the prior was having variable part just 1, so X is a beta 1, 1. Of course, X is uniform 0, 1, which is a beta 1, 1. And the conditional, the conditional density Fx given I1 is 1. We saw on the first page that this is 2x, and so in particular the variable part is x, and hence x given I1 is a beta 2, 1. And so I've just made pictures here of the prior and the posterior. So if you're told that when you flip a coin that you get a heads, you're going to want to update what the chance of heads is from just being any probability to most likely closer to 1 than to 0. So here's another example. Let A be an event and let X be uniform 0, 1. Suppose the conditional of X is X, A has probability X. Find the conditional density of X given the complement of A. So the conditional is proportional to the likelihood times the prior. The likelihood is the probability of AC given X is X, so this is 1 minus X. The prior is 1, so we just get 1 minus X. So this is X given AC is a beta 1, 2. And then you can determine exactly what the density is. So we did a concept test here. Let A and B be events and let X be a random variable uniformly distributed on 0, 1. Suppose that conditional on X is X. A and B are independent, each with probability X. The conditional density of X, given that A occurs and B doesn't, is, so the answer was beta 2, 2, and you can tell this because the likelihood probability A, B complement given X is X factorizes, and you just get X times 1 minus X, which is a variable part of a beta 1, a beta 2, 2. Another one here had a variable part that was X squared, so we had beta 3, 1. Onto conjugate pairs. So when the prior and the posterior belong to the same distribution family, for example, beta, but possibly with different parameters, we say that the prior and the likelihood are conjugate. So the prior and the likelihood being conjugate means that the variable parts of the prior and the likelihood are very similar, and when you multiply them together, they combine to give you to give you the same distribution as the prior. So, for example, if the prior X is beta rs, and y is binomial nx. Then the posterior is proportional to the likelihood times the prior. The likelihood is the probability that y is j given that x is x. Prior is just the density of x. And so the likelihood for binomial, so binomial is x to the j, 1 minus x n minus j, because the likelihood, because y is binomial. And the prior, we're told, is beta. So I've written down the variable part of the beta. And notice that the variable parts of the binomial and the beta are very similar. So when you multiply them together, you just get a beta. So I've updated the parameters. Conclusion: beta for prior and binomial for likelihood is a conjugate pair, since the posterior is beta. And here's another example. So say that n is n1, n2, n3 IID Poisson theta for unknown theta. Suppose that theta is a gamma r lambda with r lambda known. Find the posterior distribution of theta. So the conditional density is proportional to the likelihood times the prior. The likelihood is the probability that n1 is n1, n2 is n2, n3 is n3, given that theta is theta. This factors and so this factors is shown here. And then I've also written the density for gamma. And when you combine this, you see that you get a gamma. And the parameters are n1 plus n2 plus n3 plus r, and lambda plus n3 plus lambda. So gamma and Poisson are conjugate pairs with the posterior gamma. That's the show for today. See you next time.